little bit of background on me. Started in security in grad school in the early 2000s, studying rootkits and ran the Georgia Tech HoneyNet. A fun story just to kind of kick us off. When I was running the HoneyNet, we had, I don't remember how many IPs we had, but we had a block of IPs on the Georgia Tech HoneyNet that we convinced the IT department to let us run, Windows platforms and some Linux on, and you'd put a machine on there and get it hacked in about 5 minutes, and we'd reformat them and everything. And one day I was at a brewery, and my friend from the computer science department called me up and said, "Hey, what's the IP address of your HoneyNet?" And I'm like, I don't remember what it was. It was 207, I don't know. But I gave him the IP address. I remembered it by heart at that point. And he said, "Thanks." And then I went home a couple hours later to check the logs, and he had redirected a 100,000 node botnet to our HoneyNet so we could study it. And at the time, that was a big botnet, but now it's much smaller than what you could see today. But that was interesting times, and some of the ways I got into security early on. So after grad school, went to APL up in Maryland, not too far from here. Did a lot of research. One of the technologies we developed is Enigma, and that's what Jim Stevens and I co-founded a company to commercialize that product, and this is kind of falling out of that. And definitely want to thank Whitney and Matt quite a bit for their help on the feedback on this. Really appreciate that. Thanks. All right, so the first thing I want to do is talk about the need for malware analysis. And there's a couple of different groups of people that I'll talk about. The first one is SOCs. And so SOCs is basically the ultimate endpoint for why you need malware analysis. And SOC analysts perform a number of different workflows for malware analysis. So one workflow is monitoring and detection. So if you send an alert from your email to the SOC and say, "Hey, what is this?" The SOC needs to analyze that. It could be malware. They're going to have to investigate. If it is, they need to take action from there and keep that off your network. Second thing is threat hunting and gap analysis. And I would say this kind of varies from SOC to SOC, depending on how much resources you have. But if you have a SOC that has a lot more resources, then a lot of these SOCs will basically go out to the malware blogs, download the samples themselves, and they'll do their own analysis. Not just read the blog, but actually they want to go through the process and dig in deep where things working, because then they can compare that to their model of their network and identify gaps and look for things that are appearing that maybe their tools aren't catching, the cutting edge stuff. And so you're always trying to stay ahead of the curve that way. Of course, if you do have an incident, that's when malware analysis becomes extremely important in a SOC. So in the first two, it's more like a preventative, less critical. But if you get an incident, that's when you need to dig in very deep. You need to figure out, okay, what happened? What data do they potentially compromise? How do we recover from this? You're going to need to know a lot more about the malware. And then testing and validation. There's a lot of red teaming that happens in SOCs, and malware is certainly a piece of that. The second group of people that I want to talk about is actually the cybersecurity companies that develop technology that feeds into the SOC. So there's different types of companies. You've got people that will work on network defense. You've got EDR companies. You have DNS, anomaly detectors, lots of different types of cybersecurity vendors themselves. They also do malware analysis. This is slightly different in the sense that they generally care a lot more about every sample and not just the ones where there's an incident. But they need to dig in deep to every single sample so that they can study it, figure out how to feed in the information they learn about that malware into their defensive thing. So for instance, if you're a network defense system, then you're going to study the command and control parameters of how the malware is behaving and figure out ways you could potentially block that or otherwise defend against it. If you're an EDR, you're going to care more about how this thing's operating on the endpoint. And so in that case, you're going to study system calls, how Windows works, and write your formulas based on that. So these are very heavy analysis. And a lot of these companies basically have teams of people that all they do is do malware analysis, and that feeds into the product development. Threat intelligence is another thing. I won't go too much into that, but each one of these is huge, of course. We all know this. But the one thing that is kind of interesting that's kind of similar across both of these is the testing and validation. That was something that we kind of learned as we began our company, is that people had this notion of have a model of how malware works or how their network works, but this notion of validation is actually taking that, detonating it, and validating their model and really learning how this actually works, and not just, and validating your model of it. So, why is it hard to analyze malware? So computers are both simple and complex. So this is just an example of typical instructions that are in a computer. Computers are extremely simple if you look at them on an instruction by instruction basis. There's not many types of instructions. So this shows taking two numbers, multiplying them together, and then copying them to another location. And so that's what people call assembly instructions. And it's very, very simple things that you do. And this is what we learned how to do in elementary school. So it's not very complicated. So if you look at it from that perspective, you're like, well, this shouldn't be so hard. But the problem is the complexity emerges from the large number of instructions. So we had one client at one point was complaining that the start menu was really slow to open in our sandbox. And so we went on a tangent and started studying that. And this was just a brief snippet of some of that analysis. I did a 3.77 recording of the start menu, and just to get a measure of how much complexity is in that one little simple thing that you do. And it was over 1.14 billion instructions. And so that's when it's really hard to get your mind around, okay, how do we actually analyze this piece of software? How do we understand what it's doing? And you can think about that same thing in terms of malware. So that's actually what the first bullet kind of falls out of. So if you think about malware as really nothing more than software, it just has the label of malware. All this complexity comes from just how software is created. And not only that, but if you take the x86 environment and Microsoft Windows environment, these are layers and layers of complexity on top of that, and all these things are interacting. And besides that, you've got all the different libraries that are in use by the software, the encryption, the compression, optimizations, that kind of thing. But on top of that, malware does a lot of things that makes it even harder to analyze. So it can do code injection to spread across processes. It can unpack itself. It can do anti-debugging, anti-evasion techniques. All these things to make your life harder. And these kind of evolve back and forth to try and get around all the tools that we were building to keep them out of our network, and it keeps going. So that's really what the last piece here is, the arms race. So I was actually curious as to how long this has been going on, and I pulled back some example malware samples over the years and kind of realized, hey, this has actually been 50 years at this point of evolving malware. So the Morris worm is probably the most famous earlier one. People don't talk about Creeper too much, but Code Red, that was actually when I was a little bit before I was in grad school. That was when worms were such a big thing. The ROP attack at Black Hat was a really interesting turning point, because then exploits started becoming more complex. It wasn't just a buffer overflow. It was how do we have more complex execution to get your initial vector going. Emotet was a huge malware sample. It kind of introduced the notion of frameworks and people working together and all these other things. And then the last three are also kind of interesting because they're more supply chain type of attacks or things that are fundamental problems with their platforms. Okay, so next thing I want to go over is the existing approaches to malware analysis. So it's really three things I want to talk about: full reverse engineering, static analysis, and dynamic analysis. And just to give you a little bit of preview, there's so many tools out there for malware analysis that this is only a very brief representation, but you can find lots and lots, and there's lots of great videos on YouTube. You can learn all about this, lots of resources. But the first one I want to start with is what I'm calling full reverse engineering. So you can think of this as you take the malware sample, and you fully decompile it into its source code or something that's equivalent model, you get the full spec of this sample and detail exactly how it works. And I kind of think of this as the gold standard for malware analysis, because if you have a perfect specification of malware, that's the answer. That's your max you can do. It's very, very hard though, of course, because you've got to, malware doesn't just, it's not straightforward to unpack and, to disassemble from the static file. Sometimes you need to unpack it, and then you need to get around anti-analysis. It has distributed pieces to it, so now you've got all these different pieces you need to pull together. And it's also, malware knows that you're going to want to decompile it, but the way these decompilers work is that they use heuristics based on how software is created, and so then the malware can attack that and start really messing up your decompiler so that the code it's given you is actually not much better than the original binary. So there's all these nasty problems there, but still, it is the gold standard, and that's what we want to start with. But since it's so hard, and I forgot to mention, of course, the sheer cost of doing the full reverse engineering. I mean, you could spend months on a single sample. It's just not scalable, super high skill required. And so that really leads to these other ideas of static analysis and dynamic analysis. And static analysis is quite good in the sense that it helps sort through a lot of things. You can use hashes to say, okay, I've already analyzed this sample. We don't have to analyze that again. You can use, I would say Yara is probably one of the biggest things that's been revolutionary in malware analysis because of its simplicity and its power. You are able to have very simple signatures that identify different types of malware samples, and it does require some skill, but it's not full reverse engineering, and you can use that to label malware families and whatnot. Other types of static analysis, you can run strings to get some kind of idea of what this thing's got in it. You can pull out DNS or IP addresses. You can look and see what libraries are loaded. You can look and see what functions it uses. But all these things, again, it's very similar. It's that the malware writers are going to attack anything that you're going to do for the analysis. They're going to pack the sample so all these things don't really do anything. They're going to add in extra DNS names that are not actually part of the malware. They're going to dynamically load DLLs, dynamically load functions, so you can't really see that until you run it. And that's really what leads people to dynamic analysis quite a bit. And so this is where sandboxes fall into, and also this where our talk will come into in a minute. But this is kind of like the precursor of the programmable sandbox. So this is basically you detonate the sample and you look and see what it's doing during the live execution. So static is too hard to analyze, so let's run it and see what happens. So in one thing you can do is actually just use NVM tools like Process Hacker and these things, run the sample and see what processes and files and whatnot get created. Or you can send it through an automated sandbox, go get some coffee, come back, and you'll get a full report of what this thing did. So for the manual stuff on this, I would say that's very, very tedious, and that's due to all the anti-analysis and anti-debugging. So if you try and run a sample through a debugger, there's all kinds of checks that the sample can do to see, am I running in a debugger, and then you're spending all your day fighting that. So that's quite a pain for analysts. And then for this type of analysis, it's very hard to recreate exactly the same thing. So if you're stepping through a sample with a debugger, you fat finger it, hit the wrong button, now you've got to recreate that state all again. So it's a very, very tedious process. The sandboxes are quite popular in the sense that it's a simple concept. You put this sample on the sandbox and you get the report back. The challenge with the traditional sandboxes is that they are doing all this analysis live while the malware sample is running, and they have to decide ahead of time what it is they're going to look for, and they are trading how much information they can pull out of that live execution versus performance. So the more and more you're looking at what's happening, eventually you can only look at so much data, and so that gives places for malware to bypass your sandbox. So that's kind of the existing approach. So what is this new approach of a programmable sandbox? Well, it's actually a programmable sandbox with this notion called record and replay. So I want to introduce that concept first, and then we'll kind of talk about how the analysis works and some advantages. So normally, as I mentioned, with a sandbox, you detonate it, and it's extracting information during the detonation, and you have to decide, ahead of time what you're going to look for. But the idea of record and replay is that we're going to split detonation of the sample into two pieces. The first piece is the record phase, where you're detonating the sample, but you're not actually doing any analysis. The only thing that you're going to do during the record phase is record everything that's happening in that environment. In our case, it's a virtual machine. So we have a special virtual machine that allows us to record the execution perfectly from the initial snapshot. And so we don't even need to do any analysis there. We don't have any hooks into the operating system or that kind of thing. We just record enough information to be able to recreate everything that happened. And what that means is that you can do all your analysis in a replay. And you don't even have to decide ahead of time what analysis you're going to do. You can run it later, and if you think of something else, you can go back and replay it and extract additional information. So that's the basic concept of record and replay. And the types of things that you can extract are, I would say the high-level activities are very similar to to sandboxes. So it does have that same sandbox type feel to it. The network data, the files, the registry, processes, threads, all these things. But we actually have the ability to drill down much further. We can drill down into individual functions, and we can go all the way down into individual instructions. And we can also go back and recreate what memory looked like at any point in time. So if you have some kind of sample that is unpacking itself, doing some action, repacking itself so it's hard to capture what it looks like in its unpacked state, this technique solves that problem because you can just go back to an unpacked state. And then you can dump memory and use all your existing techniques to analyze the memory. This is just platform, just gives you that data essentially. And then the last one is, I'll just kind of allude to, but basically we can recreate the entire data flow of everything that's happening in those individual instructions. And that gives you the perfect model of the execution. And that one of our later demos will kind of demonstrate the types of analytics you can do with that. And so the advantages, the first advantage that's big here is that there's really nowhere for the malware to hide. The worst case scenario, the malware decides that it's in a sandbox, but it's still going to have to let you know that it's in a sandbox because you can go back and figure out what information it was probing in your sandbox to figure out it was in a sandbox, and then you can fix that up and try it again and get it to go. The other thing that I want to point out is we've mentioned lots of approaches to malware analysis. So all those tools, the industry has learned all these skills with all these tools, and they're very valuable. So you can think of this particular platform as a data source for those tools, and so you can feed those tools, the data from this to those tools, and use your existing skills to analyze the samples. And so let's look at, take this to the next step, which is the idea of turning this into a programmable sandbox. So this concept is that basically there's all this analytic that you need to be able to do, and it's going to be very custom depending on the type of analysis you're doing. And we were mentioning earlier, some people may be more interested in digging into the network data, some people may be more interested in system calls or function calls. And so the idea is to create this API that allows you to programmatically pull out any information you want. And we've kind of come up with a design that's has a few pieces to it. I'll actually start at the bottom. The one thing that we've kind of figured out, of course, is the layers of abstraction are very important here. So at the bottom layer, we have what are called primitive analyzers, where these are very low-level things like breaking on a particular instruction, single-stepping the execution, reading memory, very low-level things, but most people are not going to want to use those because that's very tedious, but you need that at the base layer. And then the second layer is the intermediate analyzers. And so this is things, we have a thing called a data flow and a backtracker. We'll show you that later. Or like a Yara scan, something that requires some skill and knowledge, but it's not as low level as, single step, that kind of thing. And then the application analyzers are probably where most people will want to live most of the time. This is going to be like very high level things like analyze sample, give me the report, extract TLS, unpack, that type of thing. But the way we've designed this particular platform is to basically open up the whole platform, and we write our analytics with the same API that would be available to people that were using the sandbox as well. So everything is available, and if you want the low-level stuff, you can recreate the same types of analytics we recreate. It's there, it's available. And then the other piece that this slide kind of gives you an overview of is 3 different API bindings. So we have the Python and Go APIs bindings are quite similar. Those are useful because they abstract a lot of things for you and give you a framework to work with. The only difference between Go is some things it's nice to have more performance, but otherwise they're quite similar. But the REST API is one of the APIs you would use more for integrations because that's just kind of the industry standard. It essentially gives you 0 dependencies. You don't have to deal with pulling in a Python API into your workflow to get the integration going. But all the APIs allow you to fully access anything that you can do with this platform. So, but REST is the main one. So here's some examples: high-level things, exporting the PCAP, TLS keys, listing created files, typical sandbox stuff, and then running YARL in memory, that kind of thing. Queuing files for manual analysis, very basic types of things to more custom analysis and more advanced stuff that we'll go into. So this is just we'll go into overview of both of the Go API and the Python. The REST and the Go Python API. So one of the innovations that kind of fell out of the REST API was we started with the Python API, but we wanted to make a REST API that was exactly like Python. So we ended up coming up with a very simple generic API design that lets you fully walk what we're calling a graph of the data. So turns out you only need a few different calls. So we have some calls to do analysis, like analyze file, analyze URL. You have one call to upload a file to the server, because you need to be able to get files to the server, and one to download. And then these 2 here are actually all you really need to walk all the data that can come out of this platform. So you can, the first one is get object, and that means like get a JSON object, and that gives you the ability to fetch the top level report. And in that report, there will be lists. And so you can, for each list, some of these lists can be very, very large, like what's the list of all instructions? That's quite large. But with this simple design here, you can just say, you could fetch them all if you really wanted to. You could, and the way that works is you just pass in an offset in the list and the number of items you want, and you just fetch that over and over again. And so that gives you a nice set of primitives to get any of the data out. And so what the data looks like, it's just a really big JSON graph, and it's self-descriptive and has this ability to get more and more data as needed. There is another notion here that I think that's pretty interesting that we came up with, which is called data tokens. So one problem is that there's so much data, even in one recording, that you just can't download the whole thing. You need to decide what it is you're interested in and download that data. And so the way that works is, let's say you run an analysis on a file, then you'll get a report back, and that'll give you a top-level summary of data. Maybe it gives you a list of processes, maybe a little bit of information about files, that kind of thing. But if you want to walk through the data from there, and let's say you wanted to see what the system calls were for a particular process, then the way we do that is we embed a data token into that process. And that data token is basically a string that's formatted in a way that it uniquely describes that particular piece of data, so you can fetch all of it. And I'll give you an example of that in a minute. But that's kind of the preview. And then the Python and Go bindings are a little bit different than the rest. And the main difference is that we basically give you, you can think of the REST API as being those simple primitives, and then you get a bunch of data. Now the advantage here is like you can read the data yourself. It's fairly self-explanatory. You don't have to learn the API. But the problem is you really kind of have to end up writing some of your own framework for certain things. And so that's what, if you're going to do something more sophisticated, the Python API is actually quite nice because we've done that work of creating the framework for you. So you can do, with a short little Python script, you can do run.record and run.replay, and now you have access to this full capability to that's behind the Renigma, the record and replay. And very simple calls here as well. So if you wanted to stop at a certain point, dump memory, single step, get the CPU state. So that's the idea of this particular call. I mean, this particular piece of the API. And then there's actually another nice piece of this design, which is we include a number of things that we call Renigma tools. You can call them just tools. It's kind of like the Unix design where you can build a bunch of small tools that do one thing specifically. And so those are built on top of the API. So a couple of the ones I listed here is the data flow, which gives you a low level information backtracker. I'm going to demo that. Or there's a tool that only thing it specializes in is system call analysis. There's another one called VAD tracer, which is kind of tracing what's happening between calls and between DLLs and the main library, the main executable. And then you can, and then of course I already kind of mentioned that there's a library of the custom tools. And then the only thing that's kind of missing here is that all these tools are designed as APIs as well. So you get the full analyzer API. So if you wanted to get the data from those tools yourself, you don't have to call that tool. You can actually just use the API. Okay, so now I want to start in on our 3 examples. So these examples are going to build on each other in terms of complexity. The first one's going to be very simple. Each one will have a video that goes with it. First, I'm going to walk through a preview of the example, and then we'll walk through the video. So start with, what's this most simple thing I can come up with? This is the code for queuing a sample into Renigma for manual analysis. And so this is actually quite useful, though, for a SOC, because in a SOC you're overwhelmed with all these alerts, all these things coming in. So anything you can do to make the workflow of analysis easier and with automation, it's great. So this would be just a way of putting together a simple tool that's pulling out stuff from your use box or other tools and queuing it over to Renigma so you don't have to copy and paste it. And so very simple code in this case. You need the API key, and then the request is just queue a URL manual and the name of the URL, and that's pretty much it. So for a little bit of a preview of the video to get started, because this is going to show you the queuing process, and then I'm also going to give you an overview of this notion of the record and replay and how this tool works. So we can go ahead and bring up the first video. Okay, so very quickly what's going to happen here is just running that script. I'm going to queue a URL. So that's the main API. It queues it over here. And at this point, it's a manual push it to start the detonation. And so in this phase of the analysis, we're doing recording. And that brings it up to a URL. You have to fight Chrome to actually get malware to execute sometimes. And then you execute it and nothing happens. So after that, you run analysis, And this is showing a visual replay. This is actually not me interacting with the system. This is just kind of showing you this notion of the record and replay. You can see everything is happening exactly as it did during the recording. All the mouse movements, the network traffic's getting replayed, exactly the same. One of our analyzers, this thing called the process analysis, is running right now. And so we speed that up a little bit so we don't have to wait on that. And then we can go look at the details for what happened for the post-analysis. And so in this case, it gives you a little summary information, got PCAP. Let's go look at the details. And so this gives you all the process information, so you can drill down and see. This particular sample actually creates a bunch of sub-processes, by the way, very noisy. And you can drill down created files, you can look and see what the sub-processes are, and then you can actually download the files that it created. So it's able to replay that execution, extract all the information about the files, and give you all that data. Okay, so you can flip back to the slides and we'll go to the next example. And so this one is the second example, so we're going to go a little more advanced this time. This is simply a fully automated analysis of a sample instead of the manual detonation. What is the API to, if you want to fully automate it? And we're also doing a file this time instead of a URL, so it's actually a little bit more of a pain because we have to, first step here in the top code is just, here's how you upload that file to the server. And when you upload that, you'll get back an ID that you can use to in the second step, which is, in this case, we're going to call analyze file, pass in the file ID that came from up here, and that starts the process of analysis. And this notion of the data token is actually everywhere. We even figured out how to make this part of the, if you're queuing a new analysis, we give you back a data token that uniquely defines that particular analysis you just queued off. And so this is an immediate call, comes back immediately, and then the server's processing. And so you need to wait until the analysis is done. And so this is just a simple loop here to check on it. And if you get a deadline exceeded, that means you need to keep going because it hasn't finished executing yet. And so for this second video, the quick preview is that basically all the action is going to happen in the terminal. I have the browser in the background just so you can kind of see that stuff's happening there, but most of it's what you care about is the terminal. So you can bring up the second video. Okay, so this is just running that script, and so not much is going to happen in here until the analysis has completed. So we speed that up and just you can and get the full report there at the end. And so this is what I meant by a giant JSON graph of data. So you've got a bunch of stuff. Let's zoom in here and look at what I mean by a token. So here's an example where we embed the PCAP token. You can use that token to download the PCAP. And then this down here is information on that particular file. It's got lists in there with data tokens that you can extract and pull down the list. So for example, here is files created, files opened. And so you can think of the data for one analysis of a sample as being, start with that one report, and you can kind of see the structure of each process gets indented and gives you a subgraph, and then each file below a process gives you another subgraph. And so we can embed these data tokens to allow you to extract more information at each of those pieces. And one of the unique things about the record and replay in this case is, and the reason the data token works so well is because once you've got that recording, you can describe any point in that graph with a string that kind of looks like a sequence of arguments. So example, let's say you wanted all the files for a particular process. Well, you can think about that in terms of a function. It's going to need an ID for the recording. It's going to need a PID for the process of interest. And then it's going to need some kind of name of the data that you're looking for. In this case, the files created or something like that. And that's how we can create a string that tells you which piece of data you're interested in. All right, so this is the third example. And this one actually is going to be much longer than the first two. It's about a 5-minute video. It's going to take a bit of time to walk through. It's going to be somewhat fast, so I want to spend a little bit of time ahead of time going over a couple of concepts because there's some lower level things here that you might not be familiar with. But the high level concept is, we're going to start with TLS data in the PCAP. And we want to see if we can backtrack all the way to the plain text for where that data was created in the malware sample before it went on the wire. And so the way that works in the operating system is to get the data out the network, there is a special thing that happens in a CPU called memory mapped I/O. And that just means you write to a memory address in the computer that's a special type of memory address. And when you do that, that actually sends some commands over to the network card and tells it, hey, here's a buffer of data. I would like you to send this out the network card. That's what I mean by MMIO. That's kind of like a low-level thing. But that's where the initial point's going to happen in terms of in the computer where this TLS data came from. That's your starting point. So the question is, can we backtrack from there and figure out where that came from? And the way computers work, by the way, is actually mostly copying stuff around. Like everything can be modeled as copying things around. Even things like multiplication and that type of thing is really just, you can think of it as modeling as just looking up in tables or kind of fancy tables and copying data to get the result. And so we can exploit that and say, well, before it got to this point, it must have been copied from somewhere. And it's going to have to get copied into the kernel, so that's what we say kernel copying. But before it got into the kernel, it's going to be copied in user space. And at some point, there's going to be what we call a definition of that data. So the data had to come from somewhere. And there's different things that can create data. Could be a computation like multiplication or addition or subtraction, but something that's a computation, and then the other ones are all move instructions that are just moving it until it gets it out the network card. So that's what we're going to look at in this demo. So we can go ahead and bring up the video. Okay, so start with, we're just going to do a visual replay again. This is a sample I downloaded and just kind of skipped ahead. Let's open up on the desktop, run as administrator. And the theme here is that nothing ever happens with malware. And then let's just go quickly look at some details. And we can see here's some fishy looking connections. Turns out they're to 443. That's what the TLS means, encrypted data. So we can download the PCAP, open that up in Wireshark. We can actually skip straight to that particular flow we're interested in, one we want to look back on. And the way TLS works, you've got a couple of stuff back and forth, client hello, server hello, kind of negotiating stuff. It actually takes a while before you get to the application data. And then let's drill down in the first actual data transport layer. Let's go into the TLS record. And so there's some of the bytes of the encrypted data. So let's make a note of the 01CB. Now we can go over to some of our tooling here. Use this thing called LSMMIO, which gives you those low-level events we were talking about. And this is actually going to show you all the writes to the network card that happened during the recording. And so this was basically based on analysis, so we pull that out. So now we can search for those bytes, and they're random, so there's not actually going to be more than one copy. And so there we go. We found the exact point in the recording where that was written to the network card. So we can take that and feed it to this backtracker, and give it the recording ID, and we have this thing called the execution point. That tells you the point in time in the recording when that happened. And so that's like a key principle here. And so we take that and say, all right, well, here's where we're going to start with the backtracker. And then you also need to know a register or a physical address in memory of where you want to backtrack from. So we go and pull out the buffer that was sent to the network card, said, hey, copy this from this buffer. And we feed that over to the backtracker. And then we kick off the analysis. And so in this particular analysis, we're giving you a little bit of feedback on what's happening. And that way you can kind of as an analyst, if you're using this kind of tool, you can kind of watch the progress instead of just waiting. And what it's doing is it starts at that first point in time, and it's backing up a little bit, and it's scanning forward, replaying the execution, looking for where that data got copied from. And you can see some of the things, it's analyzing instructions, that kind of stuff. That's to slowly back up, and it's building this graph for you. And at the very end, it's going to give us the result. It should pop up, and then we'll go into the details of that. And so each one of these long things here, by the way, is a notion of an execution point. So those numbers give you the precise instruction in that recording for that particular point. And there, it got the result for us. So let's blow this up. And there's MMIO, kernel copy, user copy, back to the malware sample with the XOR that created that particular byte of the encrypted code that got sent on the wire. So now we can take that execution point, we can use that and seek to it. First, I want to kind of start the execution here, and then scroll down here. Here's where you can take those execution points, copy it over, and do a seek, basically to go investigate and pull out more information there. This could all be scripted, by the way, as well, but it's kind of nice to visualize it here to give you the model. I'm going to back up a little bit as well, just so we can single step forward. And then this part is what it's doing is, it had saved a snapshot right here before the sample had started executing, and now it needs to replay up to the point where I launched the sample, and the sample is creating that data. And we'll stop just before that point in time where it's encrypting the data with the key that's already been regenerated in exactly the same form. And this one's actually showing you how you have to fight Windows, of course, to get the sample to execute. And then it gets to that point. And so once it gets to that point, it stops. So we have a debugger that's built in to the replay. We can single step a couple instructions and just get straight there to that particular XOR instruction. If you know anything about crypto, XORs, basically how you do a lot of the crypto algorithms. And so we can see the ESI on the right. Let's go look at that memory over here. Plain text, encrypted data. And so that's how we were able to go all the way from the data that was encrypted, went through the TLS encryption. We backtracked through the kernel copies, through the user space copy, to the point in the malware where it was doing the XOR instruction to actually encrypt that byte. And so over here we have, if you can see in the back, if you can't see in the back, this is an HTTP post for it's sending some kind of information to its command and control with that server that we identified in the PCAP, and that gives you the plain text for what this particular sample is doing and lets you uncover all the details there that you're interested in. Okay, so now we can go back to the slides, and that's the all right. Yep. So that's the idea of this sandbox, and that's the summary. So we've got these layers of abstraction. We've got this notion of the fully programmable API to pull all this information out. It's the same API we use to build that backtracker. If you wanted to build your own backtracker, you could do the same thing. We use these low-level primitives to do it. Or you could use the library that gives you the backtracker. And then basically that gives you nowhere for the malware to hide because we can see everything it's doing. So that's it. Do we have any questions?
Yeah, hi. I think being able to decrypt the stuff and find it in memory is really cool. So, but that really wouldn't be limited to TLS, right? That was just kind of an example. So if a malware family was kind of like rolling its own crypto, you could still trace back to that same point, pretty much just in the very same way that you did there. Is that right?
Yeah, and actually, there's a lot of details. Like there's a lot of variables in TLS. This particular TLS was configured with Galois counter mode, and so that actually happened to backtrack straight to that XOR. If it's a different configuration, it's going to land on a different type of thing, and you're going to have to figure that out. But I think But if the malware was rolling its own crypto, that's actually why this is really powerful, right? So like, if you ahead of time said, okay, here's all the libraries that do crypto, I'm just going to hook those and look for the crypto that way, then you wouldn't be able to see the malware if it brought its own crypto library. And so this would backtrack to that code. Now, where is it going to land? It's going to depend on exactly how that piece of malware has implemented its encryption. But it'll get you back to that code that created the data. And you may have to go back further. It may be a few rounds of different steps, but yeah, it would work.
Okay, yeah, it's really cool to be able to get there that quickly. Yeah.
Yeah, awesome. Any other questions? Everybody's ready to go to happy hour.
All right.
All right. All right.